To do this problem, you really need to focus on the words here. The words hold the key to this problem. You bought a Mobile kit, you read the package. The weight of the entire Mobile is 40 ounces. That's probably pretty important. The whole Mobile is 40 ounces. Each inch of the crossbar weighs 1 ounce. This is also critically important. We're trying to find the weight of each shape, and we need to justify our reasoning. Justifying your reasoning in this case doesn't necessarily mean a proof, but sentences are going to be good. So we're talking about it, so talking about it is going to be good enough. But you should probably try to remember or write down what we say. This is the type of problem that could easily show up on an ACT test, by the way. It tests your ability to use logic. It doesn't test anything else. All right, we have an entire Mobile is 40 ounces. What do you know about mobiles? No. Equal, maybe. There's a better word to use. They balance, yeah. So if they're balanced, then that means that what has to be true about the weight? The weight has to be the same on either side, okay? So if this thing right here is in balance, then how much weight must be on the left side and how much weight must be on the right side? How much weight must be on the left? The same as what's on the right, which means that there is how many ounces on the left? 20 and 20. The entire Mobile is 40 ounces. Therefore, there must be 20 ounces over here, and there must be 20 ounces over here. Okay? Now, if we know that there's 20 ounces over here, and the other piece of information says each inch of the crossbar weighs 1 ounce, then how many ounces are being used up in that crossbar? 4 ounces, leaving us with 16. So the orange figure is 16 ounces. Okay, now we just got to do the same sort of logical deduction for the other side. How much weight do I have total on the other side right now? 20. How much weight is in that top bar? 4, which means that this whole thing right here weighs how much? 16 ounces. We have 16 ounces to work with now. So how much does the yellow thing weigh?
5.
It's 8, 5, or 6. So if there's 16 ounces to work with, and this thing is balanced right here, then how much weight is there going to be on the right side of the figure? 8. And how much is being used up by the crossbar? 2, for giving us a total of how much for the yellow thing? 6. So if this is 8, and this is 8, and we know that the crossbar right here is how much? 2. Then how much weight do I have remaining right here? There's 6 ounces there. Tell me how much a green one weighs. How'd you get 2? The bar is 1 on either side, or 2 total, and we have 2 of those green figures. We had 6 to begin with. We're down to 4. 1 green figure is worth 2. I could see an ACT test asking you how much 1 green figure weighs, giving you only the information up here that I put up here. Would you be able to do that? Work your way through the problem? Do you think that there would be a 3 on there for a multiple choice? Or any of the other things that you guys came up with? Yeah, absolutely. Those distractors, those are called distractors. The other problems that they put on ACT are answers that you can come up with by making a mistake. They know what mistakes you're likely to make, and those are the answers that are going to be on there. so that if you make a mistake, you think you're right, unless you go back and check and figure out that you're actually wrong. What we're doing here is just balancing. A mobile deals with balance. That's something that we work with every day, or maybe not every day, but we certainly have seen it in our lives from time to time. So that's why this is up here. We're balancing things today. In our case, equations. So that's why this was brought up. And then writing equations from given information. Given information probably means what type of problem? If we're writing equations from given information. I'll let you think about that for a minute. So we should probably review the properties of equality since we're going to be working with equations. And equations have equal signs. And equal signs means we need properties of equality in order to be able to solve an equation. So, the reflexive property. The definition of the reflexive property is like looking in a mirror. If you look in a mirror, what do you see? Yourself. So if A looks in a mirror, what does it see? Good. So an example of that would be 4 equals 4. The symmetric property is very similar to another property that we've talked about, but it does not deal with an equal sign. The symmetric property is if A equals B, then symmetry tells me that B equals A. Let's see if we can come up with an example here. All right. If 1/2 equals 0.5, then what is true using the symmetric property? Good. Pretty straightforward. We'll be using that later on when we have something like 4 equals x, and instead of writing that, you write x equals 4. That is true because of the symmetric property. Okay, the transitive property. This is one of my favorites. It's been in commercials a lot lately. Let's get the transitive property written down before we talk about the commercials. Anybody know it off the top of their head? We almost used it the other day also. If A equals B and B equals something else, C, then what is true? Then A equals C, or C equals A. Same thing because of the symmetric property, that's right. So an example not mathematic would be when your cable goes out, you get bored. When you get bored, you look outside. When you look outside, you see things that you shouldn't see. When you see things that you shouldn't see, you have to disappear quickly. When you have to disappear quickly, you have to fake your own death. And when you have to fake your own death, you have to attend your own funeral as a guy named Phil Shifley. Don't attend your own funeral as a guy named Phil Shifley. Switch to DirecTV. Good. That is an example of the transitive property. All of these things were true, which means the beginning is equal to the end. If you get bored, you will attend your own funeral as a guy named Phil Shifley. Is that probably true? Probably not. Probably not true. But you get the idea in that commercial. Those commercials are using the transitive property. Mathematically, if, let's see, 2.5 equals 2.5, and 2.5 equals 5/2, then what can we say? 2.5 equals 5/2. That is an example of the transitive property. You used it a lot in geometry class, I'm willing to bet. Maybe you called it substitution, but it's not. It's the transitive property. Substitution is what? Silence. Yeah? Oh, so you're just reading the definition? If A equals B, then B can be substituted or replaced. Let's use replaced with A. If A equals B, then B can be replaced with A. So if A equals B and 5A equals 10, then using substitution, what can I say? 5B equals 10. This seems a lot like the transitive property because we're seeing the if and the then in there, but this is not the transitive property. I have A equals B here. I don't have B equals something here, and then therefore A equals that thing. I have A equals B, and then I have A a part of something else, and then I substitute in B where A was and rewrite the exact same thing. It's a subtle difference, but it is an important difference, and you need to know it. All right, then we have the addition properties of equality, or the properties of equality involving our usual operations: addition, subtraction, multiplication, and division. The definition for the addition property is, the addition property of equality is if A equals B, then A plus C equals B plus C. I'm adding the same thing to both sides of an equation, and I wind up with exactly the same result. For example, I have A equals 4. So if A equals 4, then A plus 5 equals 4 plus 5. The subtraction property of equality is very similar. If what? A equals B. Very good. So an example would be if, let's use something different than A. X equals 10, then X minus 5 equals what?
5.
No. 10 minus 5. Yes, we know it's 5. That's the idea with the subtraction property of equality. The multiplication property of equality is very similar. We start off with if A equals B again. Then what? A times C equals B times C. I'm just multiplying the same number to both sides of the equation. So for example, if X equals 6, then how about 3X equals 3 times 6, which we know is 18. And the division property of equality, very similar. We just have to add one extra little thing in there. Again, if A equals B, then and I'm going to write it like this. A divided by C equals B divided by C. That's the division property of equality. But what has to be true here? C can't be 0. That's right. So I write C not equal to 0 there. I have to say that because we don't know what C is in this definition, and we can never divide by 0, so we have to include that. All right, so if we have, if X equals 6 again, let's say, then X divided by 2 equals 6 divided by 2. Those are your properties of equality. You've been using them since Algebra 1. Nothing up here is new. You're just getting a formal definition. The formal definition is the Algebra 2. This stuff here, the stuff that you already know how to do, that's the Algebra 1. We're continuing our review of solving equations now. To find the solution of equation, isolate the variable on one side of the equation using inverse operations. What are inverse operations? So the opposite of a different operation. That's right. Give me an operation. What's that? Addition. What is the inverse operation of addition? Subtraction. Give me another operation. Multiplication. What is the inverse operation of multiplication? Division. How about another operation? Exponents. So let's pick one. Pick an easy one. Squaring. Okay, if I have x squared, the inverse of x squared would be square rooting. Those are inverse operations. They undo each other. And there are a lot more. Natural logarithms, or logarithms when you get into those. Exponential functions when you get into those. Sine, cosine, and tangent also have inverses. You've learned about sine, cosine, and tangent. What is the inverse of sine? No. That is what it shows, but what you say is inverse sine, or arc sine. It is not sine to the negative first power. Negative first power, if I have x to the negative first power, you should remember, maybe not, it becomes 1 over x. And that's not what this says right here. So it's not sine to the negative first. It's notation. It's bad notation, unfortunate notation, but that is what it says, inverse sine. Okay? So we have lots of inverse operations. We are going to solve these equations using inverse operations. It shouldn't be too difficult. Look at that first one. X plus 4 equals negative 12. What is the inverse operation that needs to happen here? Subtraction. We have addition here. I want to undo that by using the inverse operation, and I'm going to subtract 4 from both sides, because we have to keep the equation balanced. Remember the subtraction property of equality. What happened on one side had to happen on the other. So now we have 4 minus 4, which is 0. It's gone. I'm left with just x on the left, and then negative 12 minus 4 is negative 16. If only Algebra 2 was this easy. It's important to remember how to do these. So that's why we're doing them. How about the one to the right? 12b equals 18. What do we have to do there? Good, divide by 12, because what is going on here is 12 times b. We need the inverse operation to undo that. The thing that undoes times is division, so we divide by 12 to both sides, and we get b equals 18 twelfths, which reduces to 3 halves. We must always reduce our fractions. Notice how I'm showing my work here. Still show your work. Some of this stuff, maybe you can skip a couple steps. But for the most part, continue showing work. All right, next one. Negative 27 plus 6y equals 3 times y minus 3. What should we do first? Okay, distributive property to get rid of these parentheses. So when I do that, now I'm going to rewrite that whole line. And I have negative 27 plus 6y equals what? 3y minus 3. Good, minus 9. Remember to distribute to both. That's the classic mistake that people make. Distribute to both. All right, now we have the distributive property done. What do we do now? After you distribute, you should always combine like terms. So look on the left side. Do we have any like terms to combine on the left side? No. Do we have any like terms to combine on the right side? No. Okay, so we didn't have to do that. But always check to see if you can combine like terms. And combine them. That does not mean add or subtract from both sides. It means combine them. All right, so we combine like terms, now what? What's our goal? Let me start with what's our goal. Yeah, we want to get y by itself, right? Which means we need all the y's on one side and we need everything else on the other side. So try to think about where you're going. Do I want the y's all on the left, or do I want them all on the right? On the left? Okay, it doesn't matter. So now that we know that we're putting the y's on the left, what should we do? You want to move the 27 over here first? That's fine. So we're going to add 27 on both sides. And when I do that, I have what on the left? 6y equals 3y plus 18. Good. Okay, now what? Subtract the 3y from both sides. And what do we get on the left? 3y equals 18. One more step. Divide both sides by 3. Y equals 6. Circle your answer. What should we probably do now? Yeah, you should always check your work. It doesn't take very long at all. Take the 6, plug it in, you get 36 here. Negative 27 plus 36 is hopefully around 9. Take the 6, plug it in here. 6 minus 3 is 3. 3 times 3 is 9. 9 equals 9. You got it right. Okay? So this is the correct answer. Did I write anything down when I was checking? No, you could. I could have written a 9 here, just so I'd remember. But it's not important to write stuff down. It is important to check. And it's easy to check these problems. So do it. All right, let's do this one here together. Let's talk our way through it, and then I'll unleash you guys on the other two. What do we do first? Distribute. All right, help me through it. Yeah? What is that number right there? It's a negative 2. So it is a negative 2 when you distribute it as well. If you can't remember that, in Algebra 1 I taught you to do a quick change here. So now you can see that it is a negative 2. So you distribute the negative 2. So what do we have? So we'll write minus 8. Good. Equals 11x. All right, now what do we do? Combine like terms. Let's combine the x's first. What do we get? 6x minus 6x basically is 0x. It's gone. So negative 11 equals 11x. Oh, this becomes kind of an easy problem. What do we do now? Divide by 11, and what do we get as an answer? As an answer, x equals negative 1. You started with an equation, you got to finish with an equation. If you start with an expression, you got to finish with an expression. This was an equation.
You still get the same answer if you added, like,
If you subtracted 6x from both sides,
you added the negative 6x to the 6x.
we did. We got 0x. That's all right. All right, second two, or last two, sorry. Go ahead and work with the person you're sitting next to. All right, let's take a look at the first one. What do we do first? Sure, you could combine like terms. On the left side, what do you get? 3x plus 6 equals, on the right side, 3x plus 4. The way that I have that written should be a clue right now. You actually don't have to go any farther than this. But we will. What do you do now? Okay, subtract 4 from both sides, sure. And that gives me 3x plus 2 equals 3x. There should be alarms going off in your mind right now. I get 2 equals 0. And the world just exploded, right? What do? We have 2 equals 0. Is that ever true? No. So that means that no matter what I plug in for x, I will wind up with something that is not true. And therefore, we're going to say that the answer here is no solution. There was a symbol that I taught you in Algebra 1. Circle with a line through it represents the empty set. There is no solution. It means the same thing. So if you give me either of those, I'd be happy. On the second one, what should we do first? Distribute. So we have 2x. Yep. Okay. Equals. Yep. All right. Now what? Combine like terms, and on the left side we get minus 12 equals 5x minus 12. Now I'm going to stop here, and I'm going to go back to the previous problem. And I said something should have set off some sort of alarm right here. If it didn't, that's okay. But right here, an alarm definitely should have been going off in your mind. You could have stopped anywhere along here if you noticed that this was never going to be true. No matter what I plug in here, I'm going to get something plus 6 equals that same thing plus 4. Is that ever going to happen? No. Over here I have 5x minus 12 equals 5x minus 12. That's the exact same thing. This is the reflexive property. We have the exact same thing on both sides. If you continue with this problem, you would wind up eventually with what? 0 equals 0. Is that true? Yes, 0 does equal 0. Of course it does. That's like the definition of 0, right? 0 is 0. 5x minus 12 is 5x minus 12. No matter what number I plug in here, I will get a true statement. So therefore the answer here is all real numbers. That symbol, the double bar R, capital R, stands for all real numbers. You can give me either. You can write all real numbers or you can write the symbol. Don't care. The last part of this section is something called literal equations. Solving literal equations. Literal equations are basically your formulas that you've been working with from time to time. We have a formula sitting right here, C equals 5/9 times F minus 32. That is the formula for converting between Fahrenheit and Celsius. If you want to memorize that, you can impress your friends later on by telling them what it is in Celsius if they tell you that it's 70 degrees outside. So what is F in terms of C? What if they gave you the temperature in Celsius and you wanted to find out how much it was Fahrenheit? What is F in terms of C tells me to solve for F. I got to get F by itself. This is Algebra 1 stuff here. I just need to remember how to do it. So if I have to get F by itself, then I got to start picking away at F. Just like solving for X in those previous equations. We had to solve for X by slowly picking away at what was surrounding X. Here we're going to have to slowly pick away at what's surrounding F. So what's the first thing we should do? Multiply 9/5 to each side. Why multiply 9/5 to each side? What is 5/9 times 9/5? 1. And that removes this number in front of the parentheses. This is a very good way to do that. You guys are going to be doing that all year this year. So recognize when you can multiply both sides by a reciprocal rather than doing what? Rather than distributing. You save yourself a lot of time. So now I have 9/5 C equals what? Just F minus 32. And we got one more step. Add 32 to both sides. And when you do that, you get F equals 9/5 C plus 32. That's your answer. Multiplying by 9/5 there saves you a lot of time and headache with working with those fractions. All right, let's really quick make K equals C plus 273. K, maybe you haven't learned that one yet. K represents kelvins. Has anybody learned about kelvins? You did? Is there such a thing as a negative Kelvin? No. Because eventually you wind up with a temperature of absolute 0. You can't go any lower than that, and that is 0 Kelvin, right? Everything stopped. Yeah, that's right. So this is your equation for Kelvin to Celsius, or Celsius to Kelvin. Actually, it's Celsius to Kelvin. We want to switch it around so that it's Kelvin to Celsius. What do? We're solving for C. Good. So we have K equals C plus 273. Subtract 273 from both sides. And we get C equals, I'm writing this fairly sloppily, by the way. I just don't have enough room. Good. K minus 273. All right, is the above equation. We can talk about both of these, actually. Are these equations always, sometimes, or never true, the ones that we just found? Why are they always true? What'd you say? No. We're not substituting. We started with a formula right here. We started with a formula here, literal equation. It represented something, and we've taken this one to be true. So how do we know that this and this are also true? Try it.
Well, no, I'm just going to say, if you are at Celsius plus 273,
Yeah.
that's degrees, is that still nothing?
Kelvin?
Yeah.
Kelvin's Kelvin. It's nothing.
No, I'm saying it's Celsius.
Celsius is degrees, yeah.
So then you'd be adding 273 degrees to it?
Yeah. It's switching from Kelvin to Celsius. 0 degrees Celsius is 273 Kelvin.
Okay. Can you explain why it's always true?
Yes. I'm hoping somebody will come up with it for me,
Well,
though.
I was reading it, it said on one of the alpha equations
Uh-huh.
that it was always true because it has my destiny.
So it's always true because we use properties of equality to get to this. We use properties of equality to get to this. Basically, all we did was rearrange all of the stuff. We didn't change anything, all right? So that's why what we found is always true. With literal equations, with many variables, you can solve for any of the variables. And as long as you do your math correctly, what you find will also be a true formula. That's the nice things about formulas. Yeah, the properties of equality were used, which makes what we have here equivalent to what is here. It's just written a different way. That's it for the section.